In today's lesson, we are going to talk about lipids. So what can you see from the screen is the term or the word fat. Well, along with cholesterol, lipids tend to have a bad reputation in today's world, even though they are absolutely necessary to good health. So there are common misconceptions when you see or hear the word lipid or fats. Lipids, which are also known as fats, provide a major way of storing chemical energy and carbon atoms in the body. Fats also surround and insulate vital body organs, providing protection from mechanical shock and preventing excessive loss of heat energy. Now, these are just some of the functions of fats or lipids inside our body.
Lipids are a class of biological molecules defined by low solubility in water and high solubility in nonpolar solvents. Organic compounds found in living organisms that is insoluble or only sparingly soluble in water but soluble in nonpolar organic solvents. Unlike other biomolecules, lipids do not have a common structural feature that serves as the basis for defining such compounds. This image shows the structural diversity of lipid molecules. If you will notice, some are esters, some are amides, some are alcohols, some are straight chain or acyclic, some are cyclic, and some are polycyclic lipids. The common thread that ties these lipids all together is their solubility rather than structure. All lipids are insoluble in water or are nonpolar substances. There are two common methods for classifying lipids. The first one is based on their biochemical function, and the second one is based on whether a lipid can be broken down into smaller units or not through saponification reaction, which is ahydrolysis under basic conditions. Based on biochemical function, lipids are classified or subdivided into 5 categories. It can be an energy storage lipid, membrane lipid, emulsification lipid, chemical messenger lipids, or protective coating lipids. The second method for classifying lipids is based on their response to saponification reaction or whether the lipids can be broken down to smaller units or not. Let us define what a saponification reaction is. Saponification reaction is a hydrolysis reaction that occurs in basic solution. And based on saponification, lipids can be divided into 2 categories. First are the saponifiable lipids, and the second one are the non-saponifiable lipids. In our carbohydrate discussion, we learned that monosaccharides are the basic structural unit or building blocks from which carbohydrate molecules are made. In a like manner, for lipids, a building block also exists, and the most frequently encountered lipid building block is the structural unit called a fatty acid. Now, what is a fatty acid? Fatty acids are naturally occurring monocarboxylic acid. They are composed of a long hydrocarbon chain, which is the tail, and a terminal carboxyl group, which is the head of a fatty acid. In terms of carbon chain length, fatty acids can be characterized as long-chain fatty acids. These are the fatty acids containing 12 to 26 carbons, medium-chain fatty acids with 8 to 10 carbons, and short-chain fatty acids with 4 to 6 carbon atoms. One way of classifying fatty acids is based on their saturation. They may or may not contain a double bond. With this consideration, fatty acids are classified as saturated fatty acids or the SFAs, monounsaturated fatty acids or the MFAs, or polyunsaturated fatty acids or the PUFAs. What is a saturated fatty acid? It is a fatty acid with a carbon chain in which all carbon-to-carbon bonds are composed of only single bonds. Here is a structural notation for a saturated fatty acid. This specific fatty acid is called hexadecanoic acid as its IUPAC name, but its common name is palmitic acid, which is commonly used. This is an example of the expanded structural form of a saturated fatty acid. Here are other ways to represent a saturated fatty acid. We can write a condensed structural notation or a line angle structural notation. These two structures both pertains to palmitic acid, which is a long chain saturated fatty acid. Two of the most common saturated fatty acids that we will encounter are stearic acid and palmitic acid. Stearic acid is one of the many fatty acids that occur naturally in various plants and animal derivatives. It's found in such products like animal tallow, cocoa butter, and vegetable fats. When it's used in cosmetic products, stearic acid primarily fulfills the role of a thickener or hardener. Stearic acid is a substance that helps your bar soap retain its shape, just as it does in products such as candles, oil pastels, and hard candies. Stearic acid is also a surfactant and is a powerful cleanser. What is a surfactant? This is a compound that helps reduce water's surface tension, allowing it to mix with oils and dirt on the surface of your skin. Because of stearic acid, soap particles can attach to the dirt and oil on your skin, loosening them so they can be washed away with water. Stearic acid also acts as an emulsifying agent, meaning it binds together materials such as oil and water that would usually separate. If it were not for stearic acid, your facial cleansers might not stay smooth and creamy, but would instead separate like oil and vinegar in salad dressing. Palmitic acid is a white solid that melts at 63.1 degrees Celsius. As its name tells us, it is found in palm oil, but it can also be found in butter, cheese, milk, and meat. The next classification of fatty acid is the monounsaturated fatty acid. It is a fatty acid with a carbon chain in which one carbon-to-carbon double bond is present. In biochemical important MUFAs, or monounsaturated fatty acids, the configuration about the double bond is nearly always cis. The presence of this cis double bond puts a rigid 30-degree bend in the chain. So what do we mean by the cis configuration? If you will look at the structure of this fatty acid, you will notice that because of the presence of a double bond, a bend results. Now, if both are on the same side, so both of these are pointing downwards, or sometimes it can either point upward or downward, it will be a cis configuration. But for example, when one side is downward and the other side goes upward, then it will be a trans configuration. So if the two sides are pointing in opposite direction, then the configuration will be a trans configuration. But for monounsaturated fatty acids, the configuration is a cis configuration. The bend affects the physical properties of the fatty acid. MUFAs, or monounsaturated fatty acids, are a type of fat found in a variety of foods and oils. Studies show that eating foods rich in these monounsaturated fatty acids improve blood cholesterol levels, which can decrease your risk of heart disease. Research also shows that MUFAs may benefit insulin levels and blood sugar control, which can be especially helpful if you have type 2 diabetes. Now, oils or food rich in monounsaturated fats are olive oil, canola oil, peanut oil, safflower oil, sesame oil, avocados, peanut butter, and many nuts and seeds. The last classification of fatty acids are the polyunsaturated fatty acid. It is a fatty acid with a carbon chain in which two or more carbon-to-carbon double bonds are present. In important biochemical polyunsaturated fatty acids, there are about up to 6 double bonds present. Unsaturated fatty acids and double bond position. A numerically based shorthand system exists and is used to specify the key structural parameters for fatty acids. We will be using two numbers separated by a colon to specify the number of carbon atoms present in the fatty acid and the number of carbon-to-carbon double bond present. So for this example, we will represent the fatty acid as 18:3, which means that this fatty acid has 18 carbons and 3 double bonds. Now, another notation that we can add is the Greek capital letter delta, followed by one or more superscript numbers, which will tell us the position of the double bond. So for this fatty acid, we can use the notation 18:3, and then enclose in a parenthesis delta, and then the superscripts will be the position of the double bond, which are found in carbons number 9, 12, and 15. For monounsaturated fatty acids, the position of the double bond is usually in carbon 9. So what you will be seeing is their representation, for example, 18:1 and then delta 9. And for PUFAs or polyunsaturated fatty acids, the additional double bonds are usually or generally found at carbon number 12 and carbon number 15. Several different families of unsaturated fatty acids exist, and one of the most important is the omega fatty acid family. Omega fatty acids are known based on the double bond position relative to the methyl end of the fatty acid carbon chain. Double bond positioning determined in this manner is denoted by using the Greek lowercase letter omega. The first member of the omega fatty acid family are the omega-3 fatty acids. These are unsaturated fatty acids with its endmost double bond 3 carbon atoms away from its methyl end. So if you will look at this example, or at this omega-3 fatty acid containing 20 carbon atoms, here is our methyl end. Okay, if we will count from this methyl end 1, 2, 3, the first double bond appears on the third carbon atom starting from the methyl end. So that is why it is denoted as an omega-3 fatty acid. The next member of the omega fatty acid is the omega-6 fatty acid. This is an unsaturated fatty acid with its endmost double bond 6 carbons away from its methyl end. Here are several examples of the omega-6 fatty acids. So here we have an omega-6 fatty acid with 14 carbons and 1 double bond. The next omega-6 fatty acid has 18 carbons and 2 double bonds, and the first double bond from the methyl end is found on the 6th carbon. For this discussion, our last topic will be the physical properties of fatty acids. The physical properties of fatty acids and of lipids containing fatty acids are largely determined by the length and degree of unsaturation of the fatty acid chain. So in this discussion, we will consider two physical properties of lipids: water solubility and melting point. Water solubility. This physical property of fatty acids is directly related with the carbon chain length. As the carbon chain length increases, the solubility in water decreases. Short-chain fatty acids have a slight solubility in water, which is because of the polarity of the carboxyl end or the head of the fatty acid. Long-chain fatty acids are insoluble in water because of the nonpolar nature of the hydrocarbon chain, which completely dominates solubility considerations. So as the carbon chain length increases, its solubility in water also decreases. The next physical property is the melting point. The melting points of fatty acids are greatly dependent or influenced by both the carbon chain length and degree of unsaturation. So when we say degree of unsaturation, what we mean is the number of double bonds in a molecule. This graph on the right shows the change in melting point as a function of both of these variables. So as you can see, when the chain length increases, melting point also increases. Okay, so for example, here we have from 4 carbon atoms until 24 carbon atoms. As you can see, the melting point or the temperature required for the fatty acid to melt also increases. This trend is also related to the surface area associated with a longer carbon chain and to the increased opportunities that this greater surface area affords for intermolecular attractions between fatty acid molecules. From this graph, you can also observe that for fatty acids with the same number of carbons, but with increasing degree of unsaturation or increasing number of double bonds, the greater the reduction in melting point. So here we have an example of a saturated fatty acid with 18 carbons. We have steric acid, so it doesn't have any double bond. So its melting point is around 72 or 73 degrees Celsius. Now here, if we go down here, we have oleic acid, a monounsaturated fatty acid containing 18 carbons. And if you will be comparing the melting points of these two fatty acids, oleic acid has a melting point between 10 and 20. And now for linoleic acid having 2 double bonds and linolenic acid having 3 double bonds, both containing 18 carbons, their melting points are below 0. So that means that as the degree of unsaturation increases, the melting point decreases. This graph also shows that long-chain saturated fatty acids like steric acid tend to be solid at room temperature, while long-chain unsaturated fatty acids tend to be liquids at room temperature. Here is a comparison of long-chain fatty acids with the same number of carbon but with different degrees of unsaturation. The saturated fatty acid is seen as a straight-chain molecule, and when a double bond is present, it causes the molecule to bend, making the molecule occupy a lesser surface area. So here we have oleic acid having 1 double bond, and you see because of that 1 double bond, there is a kink or a bend. The more double bond there is, the greater the bending and the lesser the surface area. Now, what will be its effect on melting point? The degree of unsaturation prevents close packing and lower the melting point, therefore increasing fluidity. That is why unsaturated fatty acids tend to be liquids at room temperature because of lesser intermolecular forces of attraction compared to saturated fatty acids.